Okay, so today's meeting will be divided into two parts. I hope it's okay for everyone that I recorded. One is Guy is going to speak about the conjugate priors, how to use it to sequentially identify change in reliability of agents. And then Sam is going to speak about how to add about base factors and how to add statistical significance to the decisions when you face such sequential decisions problems. So this is our program for today. So Guy, please go ahead.
Okay, thank you, Eitan. What I'm going to demonstrate is a Colab notebook, which is an implementation of an agent that acts according to the Bayesian belief, as Eitan explained in the previous session. It's an example of an implementation with visualization of the decision making. So let's start. First of all, you see the imports. Not that important. This is the first thing that's important. The first thing is the agent's truth P, which means what is the probability that the agent is speaking the truth. In case he's speaking the truth, he will say the right answer. Is given in each step. The agent is given information, and it can either give you the truthful answer or not truthful answer. There's an 80% chance in this case that he will give you the truthful answer, and in the remaining 20%, it's a coin flip, 50-50. Either will give the right answer or he will not. We are going to repeat this experiment 700 times. Each time is given a truth value, and he gives us a value that can be true or can be false. And each time we will update our belief system according to the number of right answer he gave and the bad answer he gave. We'll start with the default values just to have a priming value. Currently, I'm saying the agent already has one truthful answer and one falseful answer. And therefore, currently the distribution is 50-50. This is what we believe according to the agent's answer. Again, it gave us one truthful answer, one bad answer. So we believe there's a chance of 50-50 of answering the bad answer. Okay, so when we start writing each data type, the inputs is either bad or good. Each iteration, the agent is given an answer, either bad or good, and he decides what does he pass along to us. As I said before, 80% that it will give the right one, and 20% that it will randomly give either bad or good. And we try to understand what is the distribution of the state of the agent's truthfulness. Okay, so step by step, for each time we start, we choose the right answer, and we get the agent's decision on it, which means, again, like I told you before, 90% will give the right answer and 50-50 in the remaining case, 80%. So each time we update it. Either it's a good answer, so we increment A, or it's a bad answer and we increment B, and we store it. And you can see that after the 700 steps, this is the distribution that you get. You can see he converged on 0.9, which makes sense. If he's right 80% of the time, he gives the right answer, and the other one is random, you can see he got the right answer. He has 90% chance of getting the right answer. And if we want to see it step by step, how it converges, this is the animation. The code became a little more complex, but it's good for the animation. Okay, you can see as it converged, starting from the original thing, which had, in this case, after the first frame, we started recording, right answer, bad one, and it's currently very skewed, but as time progresses, you can see it gets the distribution closer and closer to the truthful value. And that's it. This Colab notebook is also available in Eitan's blog, and you're free to try it and draw your conclusions. That's it. Thank you.
Thank you. Well, one interesting thing to point here, if you go back to this, notice that the beta distribution run the simulation.
Running.
So if you notice one interesting thing about the beta distribution, not only is the average being updated, but also the concentration of the mass around the average is being updated. So that's an interesting thing to notice, and you can think to yourself, oh, here's the picture. You can try and think to yourself, why is the so the Bayes rule is not only updating the average but also the concentration, and why? Try to think to yourself, why is that happening? Okay, that's an interesting thought question about this technology. Any questions or comments at this point before we go to Sam? Okay, so Sam, can you take it away and give us provide an explanation of the idea of how you add statistical rigor to this?
Yeah, sure. Let me just share. I quickly typed up something very, very quick. Sorry. Yeah. So here's the basic concept of a Bayes factor or posterior odds. So basically, as we heard, there's a way to update the parameters. So you have a given model, for example, it could be conjugate, as we heard, maybe beta, and a model consists of the estimates of parameters of a given distribution. So for example, you might, so a model, here's in the normal case, it might be the model is that mu is 5, and SD is, the standard deviation is 2. For beta, it would be alpha is something and beta is something else. And then what usually happens is that you might have an initial or a prior guess as to what the given model will be. So you might think, I think that it's a beta distribution. This is before you start collecting data. Beta distribution with alpha and beta are some numbers. Then what happens is you end up getting data, and then you can update the model. So we can evaluate what's called the likelihood function, which is basically the same as the product of the density functions. You take the model parameter estimates, and then you say you take the data up to the x's up to a given point, n, and you can basically plug in the parameter values of m into this equation. Yeah, so then basically the Bayesian analysis consists of having two different models for comparison, say M0 a baseline and a second one M1, and you can form the posterior odds, which are the likelihood. I'm trying to remember, I think it's actually the log likelihood. It's basically the ratio of the log likelihoods under the two different models. And typically, okay, so this is the posterior odds, and when you form a Bayes factor, you're also allowed to give prior odds. So you can say the prior odds are basically, again, if you're comparing two models, it's like saying, I think M0 is twice as likely as M1. So before you basically you can adjust, just like with any Bayesian distribution, you can adjust. It's basically your prior belief on what the odds are. So typically, if you don't want to assign any belief, it's just one, because you're saying the ratio, you're saying either one is equally likely. And so if the prior odds are one, the Bayes factor and the posterior odds, PO, are the same. In some of the applications I've been working on, instead of comparing specifically two different models, you might have a given initial model, and then the M1 is just basically the initial model updated with its parameters to reflect the new data. So you can end up saying by forming this this ratio, as you observe data over time, how much likely, or basically, if my new estimate is of the distribution is reflecting the new data, how much more likely is that using the new data than the initial model that I started out with? And you can basically detect a divergence from your initial beliefs in terms of M0, and seeing how quickly the data continue to reinforce that belief or not. You know, if the two things you're trying to choose between are again, if they're about equal or about equal in likelihood, this ratio will be about 1 or close to 1. And if it gets significantly far away from it, either if it gets very large, it means the alternative, a very large positive number, it means the alternative is more likely than the baseline. If it gets close to 0, which is the opposite, the reciprocal of that, it means the baseline M0 is more likely. So you can detect drift in term. What drift here is basically that the data no longer fit the initial model in terms of the this ratio becoming very large. And the good thing is that this has an explicit kind of false type 1 error guarantee that if you set a threshold C, say for example C is 100, if the posterior odds or the Bayes factor become more than 100, you'll say that the updated model is definitely strayed very far and is more likely than the baseline. That has an error, like a false error probability of 1 over 1 plus that threshold. So the higher you set this threshold, the lower your error probability is. The good thing about this is that, you know, and of course this all assumes that you can formulate a kind of likelihood function like this, which isn't always true, but is often true. Often true. You can often form like conjugate prior models for a lot of very common situations. If you can do this, this gets around a lot of the problems with repeated peaking in sequential drift analysis, where if you try to like perform some kind of, say for example, a t-test or some statistical test that depends on maybe a p-value or something like that, if you repeatedly try to test maybe every observation, whether it's the alternative is more likely than the baseline, and then you take the first time that it detected a large deviation, just by the fact that you repeatedly tested, if each of those times has a fixed error probability, because you're repeatedly testing, your overall chances of getting it wrong get very, very large, because the first time any of the times you're peaking are wrong, it'll screw up. You'll be wrong about the whole thing. So this has the advantage that you don't need to worry about that because this whole framework of updating the model with the data means that when you get more and more data, for example, with the beta distribution, if you have more and more data, say for example, you start off with alpha is 2 and beta is 2 or something like that. That means your average is going to be a half of the distribution. If now you have the same ratio of the parameters like 10 and 10, the variance gets smaller, even though the average gets is the same. So if the variance gets smaller, means your distribution narrows, and so you're more certain. So in this way, basically, if the variance always shrinks, and it kind of controls it like offsets the fact that you can peak every time by increasing your certainty. And that's one of the advantages of this.
Great. So any questions or comments about this? Please keep sharing your screen.
Oh, sorry. Okay.
Okay. So one thing, Sam, do you have an intuition? Can you give us an intuition about why it has this property that if this ratio is bigger than C, then the error probability is 1 over?
Well, I have to. Okay. Well, it's basically okay. So that it really makes sense because hold on a second. Why sorry. So I have to look a little bit into this, but
Okay.
I mean, so okay. So it has to do with the fact that, like I said, with the because this is like a ratio of likelihoods. If okay, because the variance kind of shrinks when you update the data, so that'll be the M1. The M1 is the updated in this particular case. Again, just okay. So I have to look into this, but the fact that the Bayes factor has to be very big to reject. If it's very big, the probability of like that happening if there was actually no drift, like it's kind of like the p-value logic, is very small. So it should have this inverse relationship. The bigger the threshold, the lower the error, basically the type 1 error probability of it happening.
Thank you. Makes sense. Now another question. So we had, in Guy's example, we had the agents and kind of being transferring from agent to agent, right? That could be a next step. So in the current example, Guy is only has one agent, right? And just discovering what the agent is. But in principle, we could have had two agents, and we would transfer from one agent to the other, and we would use this to identify that we went to another agent, right?
Right. So are you saying that? Sorry, I missed a little bit of what Guy was saying because I was typing this up. You're saying that the model was about the two models were two different agents, right?
No. Let's do it that way. Guy, can you bring back your screen for a second?
Yes, one moment.
Yeah, I think maybe just to explain it, I think the question is, let's say we have an agent that was changed or replaced at some point of time.
Exactly.
And yeah, that our goal is to detect the situation and try more quickly to move to let's say that we have let's say an agent whose bias was, like in Guy's example, 80% or 90% overall, and at some point of time we have another new agent which is only 60% accuracy, so actually overall quality will be 80%, and we want to detect the situation that currently the agent was changed. This
Exactly.
is based on the true story.
Exactly. Guy, if you go up to your program, to the agent definition, so this is what Danny was talking about. If you look at the agent definition,
Agent.
what the agent is doing. So with probability 80%, go to the place where you have the probability 80%.
Oh, sorry, right, okay, right. You're saying the thing you're trying to estimate is the probability that the agent is correct, right?
Yes,
Yes.
and
Okay, right.
that's what Danny was saying. The agent changes over time. So in the beginning,
Right.
it's an 80% agent, and then it goes into a 60% agent.
Yeah.
So you would be able to use this to identify that the agent changed.
Yeah, so here's something I'm still experimenting with. You should. The thing is that the way these posterior updates work is the more okay. So for example, say that you had one agent for 5 for like 100 repetitions or something like that. The data gets updated. When I mean the data, I mean the posterior distribution gets updated with that agent. And the more you observe that agent, the more kind of the variance gets smaller. The more kind of certain or the more entrenched, I would say, it gets in that distribution. So if you suddenly have a second agent who maybe their accuracy is lower, it's a little bit of a problem because because it maybe if you saw the first agent for instead of 500 for like 5,000 repetitions, it would be more firmly reflecting that agent, and then I think it would take a longer time to detect for like you'd have to observe the second agent for a lot longer because it's already very firmly in the parameters of the first agent.
Established.
And that's unless you and Eitan, this is I was trying to do this in my experiments with the API testing where I tried to have different lengths of the initial API and then insert drift. And I think it is affected. I think what you would have to do is maybe this might work. Instead of updating the posterior in terms of instead of like having a posterior that you're constantly updating according to the regular conjugate prior rules, you might want to say have some kind of weighted updating where you maybe only take the last window, like instead of it being like all reflecting since the history of time, the beginning of the time, you could just have the posterior be like the last 500 or whatever, and then it should be more. It should have less of a lag, I think. Yeah. So of course you'd have to like keep the data in a window, and it would be a little bit more calculation. But
you need to smooth that, not have like a hard, like a decaying parameter will probably work.
yeah, right, something like that. But
So we consider, I think we tried to resolve this problem, and we consider, I think, 3 alternative options.
People, I want to stress this is a non-IBM meeting, okay? Just for your awareness, okay? Danny, go on.
Okay, I wanted to understand. Let's say there are several alternatives of how we can smooth this thing. So one possibility would be to just use some sliding window, as you said, take only last 1,000 or 100 or 500 updates, and then, you know, enable quicker learning. Another alternative would be probably to assume that with some probability, the agent could be changed in each base and posterior iteration. So from your intuition, what do you think will be the most efficient or
Well, sorry.
way?
Oh, you're saying, are you saying, okay, well, okay. I'm a little confused, but
I
because
think there's a third option, which is
Yeah,
for the importance of data points to decay as they are older. So, okay.
yeah, right. I agree. The only thing is that usually you try to do this in like a streaming setting where you assume that the you don't have the full history, and that's part of the beauty of this. So I'm not sure if you could, because to do something decaying, you would have to be able to like adjust the past data, the weights on the past data, and you have to recalculate it every time. I think the easiest thing would be, like I said, to have like a window, and then you could say for example, alpha was the parameters were alpha is 20 and beta is 30 or something. You could maybe like subtract the value before the window and then add the new value, and then so you wouldn't have to like keep the whole history. I have to look into how to do this, but
Okay.
I think something like that would work.
Sounds very interesting. Okay, thank you very much for this, Danny, Guy. Any more comments? Marcel?
No comments.
Okay. Okay, great. Okay, so thank you very much, and we'll do it again next week.
Thank you, everyone.
Okay, thank you, Eitan.
yeah.
Thank you. Bye-bye.